Have you ever stopped to think about how often we see patterns, maybe two things happening together, and just assume one causes the other? It's almost automatic, right?
It really is. Our brains are pattern matching machines.
But just because things move together doesn't mean there's a direct causal link. So the big question is, how do we get beyond just seeing correlations to understanding the actual why?
Well, that's exactly what the brilliant Udea Pearl meant when he said, you are smarter than your data. Data do not understand causes and effects. Humans do.
That's such a powerful quote. It really flips the script, doesn't it? Puts us, the humans, in the driver's seat, not just the data.
Exactly. And that's our focus for this deep dive. We're aiming to move past those simple correlations, A happens with B, to really try and uncover the true causal impacts.
Right.
We'll be exploring the key ideas and, frankly, some really cool tools that let us do this, drawing a lot from, well, seminal work in applied causal inference.
Right. So our mission today is basically to unpack these tools specifically, these visual maps called directed acyclic graphs, or DAGs, and the math behind them, structural equation models, SEMs, and see how they help us figure out what's causing what, even when things look, well, messy and complicated.
Which they usually are in the real world.
Definitely. So let's start with that fundamental challenge. Correlation versus causation. The classic example always comes up.
The ice cream and shark attacks one.
That's the one. You see sales of both spike in the summer. The data shows a clear correlation.
A very strong one sometimes.
But obviously, buying more ice cream doesn't summon sharks.
No, thankfully not. The data, see, it shows what they happen together, but it completely misses the why. There's that hidden factor, right?
That's the confounding variable.
Exactly. In this case, it's warm weather. Warmer weather means more people swimming and more people eating ice cream. It's the common cause driving both.
So if the raw data can be so misleading, showing us connections but not causes, how do we get past that? What are the tools?
Well, this is where DAGs and SEMs really shine.
Yeah.
They give us a framework, a language almost, to explicitly map out these potential hidden factors, these confounders.
Okay.
And systematically untangle the true causal threads from just associations. And they're flexible, which is key. We're not stuck with just simple linear relationships.
Right, so they help us build a more realistic picture. Let's start building that picture then. Tell us about DAGs, the visual blueprint.
Okay, so imagine a map. Each point or node on the map represents a variable. Could be anything: income, education level, eligibility for a program.
Like our 401k example later.
Precisely. And then you have arrows connecting these nodes. An arrow from A to B means A directly influences B. A is the parent, B is the child.
Simple enough, like a flow chart of influence.
Sort of, yeah. But the acyclic part in directed acyclic graph is critical.
Meaning?
No loops. You can't have an arrow going from A to B and then somehow another path leading back from B to A.
Ah, okay. So influence flows in one direction, reflecting a time order or a logical sequence. You can't be your own grandpa, causally speaking.
Exactly. It enforces a clear order. And within this structure, we have terms like ancestors, all the things that influence a node, directly or indirectly, and descendants, all the things it influences.
Got it. Parents, children, ancestors, descendants. And you mentioned something about how this helps model dependencies.
Yes, the Markov property. Basically, it says that a node is independent of everything that isn't its descendant once you know the value of its direct parents. It simplifies things enormously. It lets us break down the joint probability of all variables into smaller, manageable conditional probabilities based on the DAG structure.
Okay, that makes sense. It helps contain the complexity. So if DAGs are the visual map.
Then SEMs, structural equation models, are the mathematical engine driving it.
Right. So what does a SEM actually look like? Is it just a bunch of equations?
Essentially, yes. It's a system of equations, one for each variable in your DAG, except for the ultimate root cause variables. Each equation defines a variable as a function of its direct parents from the DAG, plus its own unique bit of randomness, or noise. We often call this an exogenous shock or error term, usually written as epsilon, like O sub y.
So like net financial wealth, Y, equals some function of 401k eligibility, D, and employer match, M, plus this unique error term, OY.
Exactly. And the crucial thing is the assignment operator we use, often written as O. It signifies that the variable on the left is generated or caused by the stuff on the right, recursively, following the DAGs arrows.
So it's not just saying they're equal, it's saying one produces the other step by step through the system.
Precisely. The DAGs shows the structure, the SEM provides the exact functional relationships, and the stochastic component. They really are two sides of the same coin.
Okay, so this combination gives us a really rich description of how variables relate and influence each other. But how do we get from this description to actually saying something causes something else? Where does causality truly enter the picture?
The magic ingredient. That comes from the concept of an intervention.
An intervention, like stepping in and changing something.
Exactly like that, but often hypothetically within the model. Instead of just observing the system as it is, we imagine we can reach in and fix a variable to a specific value.
Okay, so for the 401k, instead of just seeing who is eligible and who isn't based on their job or whatever.
Right, we'd say imagine a world where we force everyone or a specific group to be eligible. We set their D variable to 1, hypothetically.
Regardless of their income or firm size or anything else that might normally determine eligibility.
Precisely. This is often called a fix intervention, building on Perl's original do operator and work by others. What's neat about this formulation is that it lets us keep track of both the variable's natural value and its intervened value simultaneously within the model. It helps us isolate the effect.
And doing this, performing this hypothetical intervention, leads us to counterfactuals, the what-if questions.
You got it. When we intervene, we generate potential outcomes, or counterfactuals, for asking why. What would this person's financial wealth Y have been if their eligibility D had been set to eligible, even if in reality it was ineligible?
So it's like exploring parallel universes defined by our intervention.
That's a great way to think about it. And this ties into what Perl calls the first law of causal inference. He argues that SEMs naturally give rise to these potential outcomes. You don't lose anything by starting with the SEM-DAG framework. You actually gain the ability to clearly state your assumptions and figure out how to identify the causal effect.
And for each specific what-if scenario, we might draw a modified DAG. You mentioned SWIGs.
Yeah, single-world intervention graphs. It's basically the original DAG, but slightly modified, to show the variable being fixed by the intervention. It helps visualize the flow of effects in that specific counterfactual world.
Okay, this is fascinating. We're building towards identifying the actual causal effect. What's the key condition we need to satisfy to make that leap from correlation in our observed data to a causal claim?
The absolute core concept here is achieving conditional ignorability, sometimes called unconfoundedness.
Ignorability. Sounds like we need to ignore something.
Sort of. It means we need to find a set of variables, let's call it an adjustment set, such that once we account for or condition on these variables, the treatment assignment, like whether someone is naturally eligible for a 401k, is statistically independent of the potential outcome, what their wealth would be under eligibility.
Okay, let me try to rephrase. If we can control for the right set of other factors, the adjustment set, then any remaining difference in outcomes between the treated and untreated groups should, in theory, be due only to the treatment itself. We've ignored the confounding by conditioning on it.
That's an excellent way to put it. If you achieve conditional ignorability by adjusting for the right set Z, then the association you see between the treatment and outcome within levels of Z actually reflects the causal effect.
Perfect. Let's make this concrete with the 401k example you mentioned. The impact of 401k eligibility on financial wealth. Remind us of the setup.
Sure. So a 401k is a common U.S. retirement savings plan, often with employer matching contributions. We want to know if just being eligible for one, our treatment D, actually causes people to have more net financial assets, our outcome, Y.
Okay. And the other players?
We have X representing observed worker characteristics like income, age, education. Then, crucially, F representing unobserved firm characteristics, maybe things like the company's financial health or how much they generally invest in employees.
The unobserved stuff is always tricky.
Always. We also have M, the employer's matching contribution rate, which eligibility might influence and which likely affects wealth. And finally, U represents other general unobserved factors or latent variables that might influence things.
And the DAGs for this, say figure 7.1 in the source material, would show arrows connecting these, like eligibility, D affecting wealth, Y directly but also indirectly through the match.
Exactly. And it would also show paths from things like income X and firm factors F influencing both eligibility D and wealth Y, potentially creating confounding. U might influence F and X too. It maps out all those potential pathways.
Right. So how do we use our tools to find the right adjustment set here? Method 1, D separation using the counterfactual DAG, the SWIG.
Okay, so D separation is the formal rule for reading conditional independencies off a DAG. A set of nodes, SD, separates X and Y if S blocks every single path between X and Y according to specific blocking rules.
Blocking rules, like if a path runs through a node in S that's a collider, or it gets a bit technical.
It does, but the core idea is blocking flow of association. Now, imagine we draw the swig for this 401k scenario, where we've intervened to fix eligibility D. We're interested if the potential outcome YD is independent of the natural eligibility D given some adjustment set.
So we look at that swig, which has both the natural D and the fixed D.
Yes. And when we apply the D separation rules to that swig, we find something crucial. If we condition on the set containing both the observed worker covariates X and the unobserved firm covariates F,
Both X and F.
then all paths between the potential outcome YD and the natural treatment D become blocked.
Ah, so FXD separates YD from D in the swig.
Precisely. Which formally means YD is independent of D, conditional on F and X. That's our conditional ignorability statement.
And the huge implication is?
We can identify the average causal effect of eligibility if, and crucially only if, we can adjust for both worker characteristics X and those firm characteristics F.
But F is unobserved. That sounds like a problem.
It is the problem. This immediately flags the potential for omitted variable bias. If you run a regression of Y on D and only control for X, the DAG tells you you're likely getting a biased estimate because you haven't blocked the confounding path through F.
Okay, that's a really clear warning derived directly from the DAG structure and D separation. What about the second method, the backdoor criterion? Does it lead to the same place?
It does. And it's often more direct because it works on the original DAG, the factual one, not the swig.
So less drawing of new graphs. I like that.
Yeah. The idea here is to block all backdoor paths from the treatment D to the outcome Y. A backdoor path is one that starts with an arrow pointing into D.
Why backdoor?
Because it represents a potential source of confounding some common cause influencing both D and Y, entering D through the back door, so to speak. It's a non-causal pathway that creates association.
Okay. So the goal is to find an adjustment set that blocks all those non-causal backdoor routes without blocking the actual causal paths from D to Y.
Exactly. The rules are, 1, the adjustment set cannot contain any descendants of D, otherwise you might block the causal effect itself. 2, the set must block every path between D and Y that contains an arrow into D.
Right. So looking at our 401k, DAG, figure 7.1, what are the backdoor paths?
Well, you've got paths like D, X, Y, confounding by worker characteristics. You've got D, F, U, M, M, Y, confounding by firm factors, operating via the match. And potentially more complex ones involving U, like D, A, F, U, X, U, Y.
Okay, quite a few potential confounders.
Yes. Now, which set blocks all of them according to the rules?
Right.
Again, it turns out that conditioning on the set F, X does the trick. X blocks the D, X, U, Y path. F blocks the paths involving F.
So both D separation on the swig and the backdoor criterion on the original DAG point to the exact same adjustment set.
Yes, that's the beauty of it. These different conceptual approaches, rooted in the same underlying logic of the SEM, converge on the same identification strategy. It tells us that if we could observe and control for both worker X and firm F factors, then the remaining association between eligibility, D, and wealth, Y, would indeed represent the causal effect.
That convergence is really powerful. It gives you confidence that you're not just finding some statistical artifact. You systematically isolated the causal pathway, assuming your DAG is correct, of course.
Assuming the DAG is correct, and assuming another subtle point, the faithfulness assumption.
Ah, faithfulness. What's that about? Is it about the DAG truly reflecting reality?
It's slightly different. Faithfulness assumes that any conditional independence we observe in the data corresponds to a D separation in the DAG. It assumes there are no accidental independencies.
Accidental, like maybe X causes Y and X also causes Z, which negatively causes Y, and the two effects just happen to perfectly cancel out, making X and Y look independent even though there are causal paths.
Exactly that kind of scenario. Statistically, such perfect cancellations are highly unlikely. They're non-generic, but theoretically they could happen.
So if the distribution is unfaithful, our data might show independence where the DAG shows a connection, potentially misleading us.
Yes, particularly for algorithms aimed at causal discovery, trying to learn the DAG structure from the data, especially with lots of variables or limited samples. It highlights that algorithms are powerful, but domain expertise and careful thought about the potential DAG structure remain absolutely essential. You can't just blindly trust the output.
Right. Human intelligence guiding the process, just like Pearl said. So where are people actually using these DAGs and SEMs in the real world?
They've been standard tools in epidemiology for a long time for figuring out causes of disease, also heavily used in theoretical computer science.
And economics.
There's been a huge resurgence of interest in empirical economics recently, building on very early work, actually. But now with these more formalized graphical tools, people are realizing how useful they are for clearly stating assumptions and identifying effects in complex economic systems.
That makes sense. Are there practical resources if people want to try this themselves?
Absolutely. There are great online tools like dagd.net and causalfusion.net where you can actually draw DAGs and have the tool check for deseparation, find adjustment sets based on the backdoor criterion, and so on. They're fantastic learning aids.
Oh, cool. So you can sketch out your causal assumptions and see the implications.
Exactly. And for those who code, there are excellent packages in R, like DAGD, and in Python, like pgmpy or DOE and its underlying DOSearch, that let you perform these analyses programmatically.
So the tools are definitely out there to get started.
They are. So to kind of wrap things up, we've seen how DAGs provide that visual map of our causal assumptions, and SEMs give the underlying mathematical structure.
And tools like deseparation and the backdoor criterion act like formal procedures, almost like logical proofs, to figure out if and how we can isolate a causal effect from observational data by adjusting for the right confounders.
Precisely. It's about moving from just seeing the things happen together to rigorously understanding why, by carefully accounting for the potential confounding pathways identified in our causals graph.
It really forces a level of clarity about your assumptions that you might otherwise gloss over. Thinking about that 401k example, the complexity hidden beneath a seemingly simple question is quite striking.
It is, and it makes you wonder, doesn't it? If we can use these methods to untangle causality in areas like finance or health, what other important causal links might be hiding in plain sight within the data all around us? What unseen mechanisms could we uncover, and how might that change how we approach problems?
That's a really thought-provoking place to end. If we get better at asking why and have the tools to find robust answers, the potential seems enormous.
Definitely. So we really encourage you, our listeners, to explore causal inference further. Check out those resources, maybe try mapping out a causal problem you're interested in. It's a powerful way of thinking.